So what's going on, guys? Let's keep going, okay? Where were we? We were right here, right? Where did we just talk about? Oh, okay. So remember this condition, okay? Ax equals lambda x. Lambda, eigenvalue. X, eigenvector. That condition right here, Ax equals lambda x, same thing as this condition right here. A minus lambda I is the identity matrix, x equals 0, okay? And look, the solution set to this equation, this homogeneous equation, is known as a null space, right? But in this particular scenario, for this special case of A minus lambda I x equals 0, the solution set of this equation is called the eigenspace, okay? Not the null space, the eigenspace, okay? And the eigenspace is a subspace of Rn, okay? Rn. I don't think this is important. I mean, I'm really just interested in conceptual understanding, okay? I'm not worried about the details, and these videos will only detail the concepts, okay? Because I think if you master the concepts, then you can pick up the details later. You have A equals this matrix right here. Let's move on to example 4. You have an eigenvalue of A is 2. They want you to find a basis for the corresponding eigenspace, okay? So look, you form this A minus 2I thing, you get this matrix. Now you have this system right here, A minus 2I x equals 0. You form the augmented matrix, you row reduce. Okay, so at this point it is clear that 2 is indeed an eigenvalue of A. Why is this clear? Because once again, this has free variables. And generally, when you're in this form, right, and you solve the system, you solve this equation, and if there are free variables, then you know that lambda is pretty much an eigenvalue, okay? And lambda is good. So now right here, we have this form, right? And because there are free variables, we can form this linear combination right here of the free variables, and from these we can see that the corresponding vectors right here are the basis vectors, okay? That's all it is. Look, now we move on to theorem 1. The eigenvalues of a triangular matrix are the entries on its main diagonal, okay? That's just something that you can memorize, really. I'm not going over the proof. I don't think that this concept is too hard. Look, A, what are the eigenvalues? You have 3, 0, 2. B, what are the eigenvalues? 4, 1, 4 and 1, okay? Because this is a 4, so it really doesn't do anything, right? And by the way, I just want to go back for a minute and never mind. I don't know what I was doing. Sorry. And then, okay, so what happens when we want to evaluate an eigenvalue of 0, right? So look, Ax equals lambda x, well, lambda is 0. Ax equals 0. Okay, this is the same thing as Ax equals 0, which has a non-trivial solution if and only if A is not invertible. Therefore, 0 is an eigenvalue of A if and only if A is not invertible, okay? This condition of a non-trivial solution dates back to the definition, and I already read the definition, so if this doesn't make sense, read the definition, okay? I'll read this again. Thus, 0 is an eigenvalue of A if and only if A is not invertible. Okay? So now we move on to theorem 2. If V1, Vr are eigenvectors that correspond to the distinct eigenvalues lambda 1, lambda r of an n by n matrix A, then the set of eigenvectors is linearly independent. That's theorem 2, okay? I won't go over the proofs. So now we come to the last part of the chapter. What does this, let me just read this. You have this x sub k plus 1 equals a x sub k equals 0, 1, 2, infinity. If A is an m by n matrix, then A is a recursive description of a sequence x sub k in Rn. A solution of A is an explicit description of x sub k whose formula for each x sub k does not depend directly on A or on the preceding terms in the sequence other than the initial terms x naught. Okay? That's all for now. I'll post another video soon. Thank you very much.